Let's look at one more example problem dealing with energy. Do all the same things in this question that I did in the previous example. But let's say there's a bridge over a deep gorge, and you've got some daredevils who jump off of the bridge. They're tied to a long bungee cord, just some very, very elastic cord. And when that cord stretches, of course, like any elastic object, when it stretches, it's going to apply an elastic force. It's going to act just like a spring. When the cord stretches, it's going to be pulling back on the person who's jumping and make that person slow down and eventually come to a stop. So the cord itself is 40 meters long, and when it's brought the person to a stop, it has been stretched another 20 meters. So that means that when the person is at the end of the fall and has come to a stop, there's a distance of 60 meters between the bridge where the jumper jumped from and the point down here where the lowest point that the jumper gets to. 40 meters of just normal cord and then stretching 20 meters. And our question is, since the force, kind of a spring force, for that cord, what's the K value, the so-called spring constant for that cord? We can think of this problem in terms of energy. That's really a more straightforward way to do it than in terms of forces and Newton's laws. So in that case, we start the same way. First, we ask, since energy is a property of a system, what's in the system? What ought to be in the system? And remember, we have 4 rules for that. Things that are moving, they've got kinetic energy, so that has to be included in the system. So the person is moving, we have to include the person in the system. Second, the person changes elevation, which means gravitational potential energy changes. And whenever that happens, we have to include the Earth as part of the system, because the gravitational potential energy is shared by the person jumping and the Earth. And unless we include the Earth in the system, we cannot say that gravitational potential energy is actually part of the system. And then we had a third rule. Anytime an elastic object gets stretched or squeezed, we have to include that elastic object in the system because it's got some elastic potential energy. And in this case, the cord is being stretched, so that's included as part of the system. All right, now, next step, what forces are acting on the most important part of the system here, the thing that's moving, the jumper. While the jumper is falling at various times during the fall, there is, of course, the jumper's weight pulling down, and then pulling back up is the spring force from the bungee cord. While the jumper falls, there's also a drag force as the jumper is moving through the air. But to keep things relatively simple, even though there is a drag force, and like all drag forces, it's opposite to the direction of motion, to keep things relatively simple, we'll say it's pretty small compared to the other forces. So these are the only forces that matter. And then remember, we have to ask, are those internal forces or external forces? This comes from the cord, which is part of the system, so it's internal to the system. Comes from some part of the system and it acts on some part of the system. This also is an internal force. It comes from the earth, so it comes from something that's in the system and then acts on the person also in the system. So entirely internal. Remember why we want to distinguish internal from external forces. We do that because work done by external forces, and only work done by external forces, will change the energy of the system. But in this case, there are no external forces, so there can be no work done by external forces. And since no work is done by external forces, and the amount of work done by external forces is the amount of energy given to or taken from the total energy of the system, since this is zero, then that's zero. But of course, entirely within the system, different types of energy might increase while others decrease in order to keep the total constant. What is changing here? Could be as many as 4 changes. We've got the kinetic, gravitational potential energy, elastic potential energy, and then changes in thermal energy. Well, for kinetic, when the jumper just stepped off the bridge, the jumper just stepped off, for all practical purposes, had no velocity, an initial velocity of 0, and then of course when the jumper has come as far down as the jumper will go, and the jumper isn't continuing to move down, the jumper has stopped falling, so at that point the final velocity is 0 again. So there's no change in the kinetic energy between the start and the finish. At the start, there was 0 speed, so 0 kinetic energy. At the finish, there's 0 speed, so 0 kinetic energy. Gravitational potential energy has a negative change. It decreases. A change that is less than 0 because there's a decrease in elevation. And if elevation decreases, gravitational potential energy decreases. If elevation increases, gravitational potential energy increases. Okay? And then this increases. There's a positive change in elastic potential energy. Remember the rule for elastic potential energy, 1/2 K, this K, times the square of a displacement away from equilibrium. That is, if the cord is in equilibrium, it's not feeling any net force. In other words, it's not being stretched or compressed. And at that moment, it's going to be 40 meters long. But the bottom end of the cord, which will be 40 meters below the top, when the cord is all unfurled but not yet stretched, then the jumper continues to fall and the cord gets stretched by 20 meters. So the bottom of the cord experiences a displacement away from its equilibrium location of 20 meters. So initially, at the top, the cord isn't stretched, so the end of the cord isn't stretched away from its equilibrium location. So that's 0 at the start, and then it's 20 meters at the end when the cord is entirely stretched out. And then finally, there are no friction or friction-like forces. So friction, work done by friction, or work done by friction-like forces, such as a drag force, those are the thing, work done by those forces is what changes the amount of thermal energy. But we're saying that the only friction-y force, the only friction-like force, the drag force, is really small, so it's not going to do any significant amount of work, so it can't change the thermal energy very much. We'll just call it zero change. So now the next step is to, we've got the left-hand side of the equation equals 0, and then the right-hand side there are some zero terms and some non-zero terms, and the next step is to rewrite those non-zero terms in detail. That is, write them out. Use the equation for gravitational potential energy to write this out. Use the equation for elastic potential energy to write this out. So let's do that. So change in total energy is no change at all, and that's equal to this was 0, so we don't have to bother with zero terms. This term is not 0, so we'll write it out. Change in gravitational potential energy is final gravitational potential energy minus initial gravitational potential energy. Right, the rule for gravitational potential energy is just m times g times elevation. And then we have to write this out in detail. Change in elastic potential energy is just final value minus initial value. And so change is final value ½ k times the amount of displacement or stretching in the final state minus initial elastic potential energy, ½ k squared the initial displacement or stretching. Well, we can simplify that a little bit more, because here's our here's the ravine, and then the cord and the jumper, and 60 meters between the top and the bottom. There's the initial elevation, there's the final elevation, and we're always free to choose the 0 point of elevation anywhere we like. So we'll choose the bottom as the 0 point of elevation, and then positive is in the upward direction. So this value of elevation will just be plus 60 meters. And since the final value of elevation is 0, that term is 0. And since in the initial state there is no stretching, that the end of the cord is not displaced away from its equilibrium position, the initial amount of stretching is 0, so the initial amount of elastic potential energy is 0. So the equation now reduces to something relatively simple, and at this point we'll put in the numbers. And that'll look like this. 0, the change in energy, is equal to this term, mgh initial gravitational potential energy, plus 1/2 K final amount of stretching squared. Or this is the thing that we're trying to solve for. So add MGHI to both sides of the equation, and we have MGHI equals 1/2 K amount of stretching in the final state squared. Now let's put in the numbers. Let's say this jumper has a mass of 80 kilograms. Let's say the jumper has a mass of 80 kilograms. And then G, of course, is 9.8 meters per second. And the initial height, the initial elevation is 60 meters. And then 1/2 times K, and then the amount of stretching squared, the cord was stretched 20 meters. The displacement of the bottom end of the cord was 20 meters below its equilibrium point. So 20 meters times 20 meters is 400 meters squared. 1/2 of that is 200 meters squared. So what do we end up with? The right-hand side here is 47,040 joules. Right? This is a gravitational potential energy, so it comes out in joules. And then this will be 1/2 times 20 squared, 1/2 times 400, so that's K times 200. Meters times meters, because we squared some number of meters. And so K then is just 47,040 divided by 200. And the final answer that we come up with is 47,040 joules over 200 meters squared, because we squared a length. You would be surprised how easy it is to forget the square here when you're actually doing a calculation. So don't forget. That actually works out in exactly the correct kind of units, because 47,040 joules, a joule is the same as a Newton times a meter. And so divide that by 200 meters squared, and we come up with 235. Treat the unit labels as if they were algebraic variables, so this meters cancels out one of the factors of meter in the denominator here, and you're just left with newtons per meter, which is the correct unit label for K. What this means is that it takes 235 newtons of force to stretch that cord 1 meter. Just one aside here, just thinking about the where the jumper actually winds up at the end. The jumper has fallen to that level 60 meters below the bridge, but won't stay there. At that point, the velocity is 0, but the acceleration is actually not 0. How do we know the acceleration is not 0? Well, go back to the two forces on the jumper, weight, m times g, and then the spring force, which is just the magnitude of that is just k times the displacement of the bottom end of the rope, or the amount of stretching. Well, let's compare the sizes of those two things. This is 80 kilograms times the usual 9.8 meters per second. So that comes out to 784 newtons. K, remember, was 235 newtons per meter, and then the amount of stretching was 20 meters. So 235 times 20 is 4,700 newtons. In other words, the upward force is a lot stronger than the downward force at that moment when the jumper has come to a stop. So the upward force is stronger than the downward force, means the net force points up. So the jumper isn't going to stay stationary down there with the 20-meter stretching. The jumper will be pulled up, and finally, wherever the jumper comes to equilibrium, where the jumper comes finally to a stop and stays stopped, that's going to be somewhere closer to the bridge than 60 meters. But we can figure that out. So when the jumper is in equilibrium, at that point, the net force on the jumper is, of course, 0. That's one of the things that equilibrium means, which means those two forces are now equal to each other. The upward force cancels out the downward force. So K times the amount of stretching in the final state where the jumper has finally come to a stop and stays stopped is just precisely equal to the weight, which is 784 newtons. So so the amount of stretching when the jumper finally comes to a stop and stays stopped is just mg divided by k. And we knew this was 784 newtons. This is 235 newtons per meter. So the final answer will come up to 3.3 meters. The bungee cord is stretched only 3.3 meters when the jumper finally has stopped moving. Right, much less than the 20 meters of stretching that it took to stop the jumper's fall. Okay, so on the final exam, there will not be any questions dealing with anything beyond this. There's enough ideas already. No reason to add to pile on even more. So some questions about equilibrium and torques, some questions about momentum, some questions about momentum and impulse especially, and then questions about work and energy, and then a problem or two like this, the multi-step sort of analysis of an energy situation. Okay, that's it. That's everything.